All right, getting into our third lesson here in our unit about finding sequences. Looking at this warm-up, local bank has agreed to donate $250 to the annual turkey fund to help feed families in need. In addition, every bank customer every bank customer that donates, $50, the bank will donate $50. So number one here says a sequence describes the relationship between the number of $50 donations and the amount of the bank's donation. Is the sequence arithmetic or geometric? Well, considering we are just adding a number each time we have another customer donate, the bank is adding another $25. This sequence would be arithmetic. I'll draw a little arrow down here. How can you calculate the 10th term in the sequence? Well, we would take the 9th term and add $25. And what is the 20th term? Well, if we were to continue to sit there and add $25 and $25, if we had kind of a little table here, after one customer, we'd be at 25 plus the original 50. So at 0, we're at 50. At 1, we're at 25. So add to 75 and so on. We'd eventually get to the 20th term. And for the 20th term, if you keep adding 25, we would end up at $725. All right, so we're going to look more about how we develop these sequences, different formulas we can use. So moving to the next page where it says getting started. It says why common ratio or common difference can help you determine the next term in a sequence. How can they help you determine the 1,000th term in a sequence, the 10,000th term in a sequence? That might take you a long time if you're going to sit there and add that number over and over again. Okay, so this says Rico owns a the sporting goods store. He has agreed to donate $125 to the Centipede Valley High School baseball team for their equipment fund. In addition, he will donate $18 for every home run hit during this season. The sequence shown represents the possible dollar amounts that Rico could donate for the season. So starting at $125 that he's going to donate, and then each home run for there, he would add to that $18 per home run. So which sequence types does this describe? Well, again, we're just adding a same amount each time. So it is an arithmetic sequence. Describe the common difference or common ratio. Well, the common difference, because we're adding a number, put common difference, is $18. Every time the home run is hit, another $18 a time. So if we want to complete the table that would go along with that, for no home runs hit, he's donating the original $125. And then as we go up, once we'd have one home run hit, now we'd add another 18. We get to 143. And we would keep adding 18, and it would fill in these numbers in our table here. 269 and another 18, we'd be at 287. So we're just adding 18 each time to add to every new home run gets another $18. And 4, explain how you can calculate the 10th term based on the 9th term. Well, if we know the 10th term, if we know the 9th term, we would just add $18. And that would give us the next term in the sequence, no matter which term we're looking at. If we add another 18 to the previous term, we're going to get the next term in the sequence. All right, moving on to the next activity here. All right, so a recursive formula. It expresses each new term of a sequence based on the preceding term in that sequence. Okay, that's what we were just using on the last page. We were adding 18 each time to the previous term. So a recursive formula to determine the nth term in a sequence is a sub n, meaning whatever the nth term, that's what we're trying to find, is equal to the previous term. When you see a sub n minus 1, n, remember, is the term number. So it's saying whatever the value of the previous term number is. When we say n minus 1, we're looking at the previous term, plus the common difference. So if we want to know the fifth term, we take the value of the fourth term, and we're going to add the common difference to it. So in that worked example there, consider the sequence -2, -9, -16, -23. You can use the recursive formula to determine the fifth term just by taking the value of the fourth term, which in this case was -23, and adding our common difference of -7. So this is what this is showing you right here. This is saying the value of the term before the fifth, so the fourth term, which was -23, and then adding that common difference of -7 to get to -30. Okay, moving down to the below that box says, consider the sequence showing Rico's contribution to the Centipedes baseball team in terms of the number of home runs hit. So 1, use a recursive formula to determine the 11th term in the sequence. Explain what this value means in the terms of the problem situation. Well, if I want to know the 11th term, our formula would look like this. So the value of the 11th term, a sub 11, is equal to the 10th term plus 18. And if we take the 10th term in our sequence, if we go back to our table, that was 287. So if we add 18 to that, we are now at 305. So there would be the value of the 11th term in that sequence. So 2, is there a way to calculate the 20th term without first calculating the 19th term? There is. It's a little more work to come up with our formula. That's what we're going to be looking on the next few pages. But in terms of what we know already, the only way we could do that would be to keep adding 18 until we get to the 19th term. Okay, moving on to the next page. It's where we get into what that last question was leading us to. All right, so you can determine the 93rd term of a sequence by calculating each term before it and then adding 18 to the 92nd term. That's going to take us a long time. And more time it takes each row, you're more likely to make a mistake as you continue to add 18. So a more efficient way to calculate any term in a sequence is to use what's called the explicit formula. So the explicit formula doesn't require you knowing what the value of the term before it was. So an explicit formula is a formula to calculate the nth term of a sequence using the term's position in the sequence. So in other words, the term number. The explicit formula for determining the nth term of an arithmetic sequence is the nth term is equal to whatever the value of the first term is, plus the common difference times the previous term number. Not the previous term number's value, but the previous term number. So in other words, like this example is showing us down here, if we want to use the explicit formula to determine the 93rd term in this sequence, I'm going to take, and we're talking about the home run situation, we're going to take the original first value, $125. That was his original donation, remember? And he was going to add 18 to that to each home run, plus 18 that he's adding to each home run, times, we're trying to find the 93rd, so we take 93 minus 1, so times the 92nd term number. And if we simplify that and calculate 125 plus 18 times 92, we're going to get that the 93rd term number in that sequence is 1,781. Now, that would take a lot longer to get to by taking the first term and just continuing to add 18 over and over again. So that is the advantage of using the explicit formula. Okay, that's what we're going to explore more so in the next few pages. All right. So keep in mind here, the home run number isn't necessarily the term number. So if I go back to this page where we had our table, the number of home runs, like let's say 5, was always 1 lower than the term number. So the 5th home run was at term number 6. So we need to keep that in mind as we write our formula here. So for 35 home runs, we would have 125 plus 18 times, so 35 home runs would be at the 36th term number. So 36 minus 1. And if we simplify that one, we are going to get $755. So for 48 home runs, they'd all look just like that. So 125 plus 18 times 48 would be the 49th term. So 49 minus 1. And for that one, we would get $989. Now would probably be a good time to pause the video, see if you can fill in C and D, and then unpause it and see if it matches to what your thinking was. So for C, I'd get 125 plus 18 times 86th home run would have been the 87th term number, so 87 minus 1, and that one would come out to be 1,673 once you simplify it. And then for 214 home runs, 125 plus 18 times, that would be the 215th term number, so 215 minus 1, and that one would come out to be 3,977. So hopefully those matched up with what you were able to get. Okay, so it says Rico decides to increase his initial contribution and amount donated per home run he hit. He decides to contribute $500. So there's our new initial amount, and he will donate $75 for every home run the Centipedes hit. So write the first 5 terms of the sequence representing the new contribution he will make. Well, if 0 home runs are hit, he's at 500, and he's going to add 75 to that. So 575 plus another 75 would be at 650, plus another 75 would be at 725, and plus another 75 we would be at 800. So if we want to determine now based on these next two, I'm going to do A, and then again would be a good time to pause after A, and you try B. So 39 home runs, his initial was 500, plus his donation now, our common difference is 75. And again, 39 home runs would be the 40th number in the sequence. So 40 minus 1, so times the term number in front of it. And if you were to calculate that, we are going to get 3,425. And then for 50 home runs, again, if you haven't yet, pause the video, try to write this one out. So for 50 home runs, I would get 500 plus 75 times. 50 is now the 51st in the sequence. So 51st term number, I should say. So 51 minus 1, and that comes out to be 4,250. All right, moving on to our next activity. 3.2, and it says, when it comes to bugs, bats, and spiders, are there any other creepy crawlers? Finding one in your house is finding one too many. Then again, when it comes to cells, the more the better. Animals, plants, fungi, slime, molds, and other living creatures are composed of eukaryotic cells, if I pronounce that right. During growth, generally there's a cell called the mother cell that divides itself into 2 daughter cells. Each of those daughter cells then divides into 2 more cells, and so on. So the sequence shown would look something like this. The one mother cell and then times 2 each time to get the next cell number. So for A, is this geometric? Or why is this sequence geometric? And identify the common ratio. It's because it's multiplied by a common ratio. Of 2 in this case. So R equals 2. Let me rewrite that. My pen blurred a little on me there. So R equals 2. So complete the table of values using the number of cell divisions to identify the term number and the total number of cells after each division. So again, There's one cell when there's no cell divisions yet. That's term number 1. And then as we increase our term numbers, we are going out and multiplying that by 2. So then you'd be at 2, 4, 8, 16, and we just keep multiplying by 2. Until we get to 512 in that 10th term. So C, explain how you can calculate the 10th term based on the 9th term. Well, we can calculate the 10th term by multiplying the 9th term by 2. And that is using the recursive formula. Okay, which is what we're going to talk about as we flip over to our next page here. So the recursive formula to determine the nth term of a geometric sequence is the value of the previous term times the common ratio of 2. So that's the value of the previous term. I'm going to put value in front of where it says previous term because we're not talking about term number with the recursive formula. We're talking about the value of the previous term and then multiplied by that common ratio. So it says consider the sequence 4, 12, 36, 108. You can use the recursive formula to determine the 5th term in the sequence by taking the value of the 4th term, which is 108, and multiplying it by 3. And that'll give us the 5th term in the sequence, which is 324. Okay, so consider the sequence of cell divisions and total number of resulting cells. Write a recursive formula for the sequence and use the formula to determine the 12th term in the sequence. Explain what your result means in terms of this problem. Well, the recursive formula would look like this. The 12th term, putting g of 12, equals, in this case, the 11th term, if we were to keep calculating out, would be 1,024 times 2. Okay, and if we were to simplify that, we're going to find that the 12th term is 2,048 cells after 11 divisions, which is the 12th term. Because remember, our term number is always 1 higher than the number of divisions in that case. All right, moving down to the next page, we're going to look at the explicit formula for this. So the explicit formula to determine the nth term of a geometric sequence is the first term, that's where it says g sub 1, times the common ratio raised to an exponent of the previous term number. So it says you can use the explicit formula to determine the 20th term in this situation. So the first term was 1. If we look back at our table, the first term number was when we had that 1 mother cell, and then times 2 raised to an exponent of 20 minus 1. So it'll turn into, 2 to the exponent of the value of 20 minus 1. So the 20th term minus 1, the previous term before it. So we end up with 1, I underlined right over it. We end up with 1 times 2 to the 19th power. And if we simplify that, we're going to end up with 524,288. Okay, keeping that in mind, it says use the explicit formula to determine the total number of cells for each number of divisions. So again, remember, 11th division is the 12th term. So if we're going to use our formula, the first term is 1 times 2 to the 12 minus 1, which will give you 11. And if you simplify that one, we get 2,048. So for 14, we'd have the first term number. 2 to an exponent of 14 divisions would be the 15th term, so 15 minus 1. So to an exponent of 14, and that would give us 16,384. So again, now would be a good time to try to pause the video, see if you can fill in C and D, and then unpause it and see if it matches what we get here. So for the 18th, we'd have 1 times 2 to the 19th term minus 1, because 18 divisions is at the 19th term. And if we simplify that one, we should get 262,144. And then for 22 divisions, you'd have 1 times 2 to the 23 minus 1, so to the 22nd power. And that's going to give us a nice big number, 4,194,304. All right, so suppose that a scientist has 5 eukaryotic cells in a petri dish. She wonders how the growth pattern would change if the mother cell divided into 3. Well, the first 5 terms of the sequence, she'd start out with the 5 original, and if we multiply by 3, we're going to end up at 15, 45, 135, and 405. Okay, determine the number of cell divisions in a petri dish for each of these terms. So 13, original number is now 5. Common ratio is 3. And remember, 13 divisions would be the 14th term. So 14 minus 1, we're going to end up with an exponent of 13. And when we do that, you'll end up with another nice big number of 7,971,615. And then for 16 divisions, it looked very similar. 5 times 3 to an exponent of, that's now the 17th term. And even bigger result here, we're going to get 215,233,605. All right, activity 3.3. This is something you should go try on your own, referring back to our previous lesson. So the previous lesson, we were just looking at sequence patterns. It was the last couple pages in that lesson. We were just determining what the common ratio was. It says go back to those, write the recursive and explicit formulas for each sequence. There were sequences A, B, C, E, F, H, J, K, and M, I believe it was. Okay, but you can go back, try those, see if you can write the formulas for those. Okay, and then ending with last page here, just pros and cons. So what would be the advantages and disadvantages of using the recursive formula? The pros: enables making sense of a growth pattern of a sequence. Cons, the disadvantages, is it's not easy when determining term value for a large term number. In other words, if we're just going to use the recursive formula and add or multiply by the same number times the previous term, if we get up to trying to find the 1,000th term, it's going to be not efficient to go calculate that for each term to get to the one we're trying to find. Okay, and then explain the advantages and disadvantages of using the explicit formula. Pros: it's more efficient for finding value of a large term number. Cons: it is more difficult to determine an explicit an explicit formula.